Hello, this is the video for AP Calculus section 4.2. We're talking about area. We spent section 4.1 finding antiderivatives, and actually this topic today will not appear to make sense that it comes right after finding antiderivatives. Today's topic will not appear to be about antiderivatives, but what we'll learn in the next section or two is kind of how it all ties together very nicely. So this will appear to be out of place, but trust me, it's not. So one of the things that I told you on the first day of school that calculus would allow us to do is to find areas of unknown shapes. And we know how to find areas of rectangles, parallelograms, trapezoids, triangles, circles. But if it's just some generic function, a trig function, or a parabola, and I want to find area underneath the curve, we don't know how to do that yet. Turns out calculus will do that for us. But in this section, we're actually going to approximate areas. And we're going to use rectangles or trapezoids to do that. And so what I've got here is 4 different approximations that we are going to use. We're going to use what's called a left endpoint approximation and a right endpoint approximation and a midpoint approximation and a trapezoid approximation. Those will all make sense as we go through this lesson. So again, we're trying to find the area of an unknown shape. We're going to approximate the area of an unknown shape using shapes whose area we know. So as the example for today, I've got this curve, f of x equals 5 minus x squared, just a parabola all the way down. So approximate the area under the curve, f of x equals 5x minus x squared, above the x-axis from x equals 0 to x equals 2. So the area we are trying to find is all of this, like all this. That's the area we're trying to find. Okay. And we don't know the exact area yet, but we're going to approximate the area using rectangles. So this first example, I mentioned on the last slide, we've got 4 different approximations. This first one, we're going to find what's called the left endpoint approximation. So it says, here's how this process works. We're going to divide the region into 5 subintervals. Nothing magical about 5. The problem will tell you how many intervals to create. And then based on those intervals, we're going to find areas of rectangles, and we're just going to add together the area of those 5 rectangles, and that will be our approximation. It might be an under approximation, it might be an over approximation, depends on the function. But we're going to find the areas of 5 rectangles. So if we're going to do this first with the left endpoint approximation, so what I'm going to do here is I'm just going to draw some vertical lines down. Oh, didn't mean to make that an arrow. And let's see, it says 5 subintervals. And so from 0 to 2, I think each one's going to be 0.4. I think this, if I draw lines there and there and there and there and there and there, like there's that was supposed to be a vertical line. There's 5 subintervals. I still don't have rectangles. I'm going to create rectangles. So the question is, how tall is each rectangle going to be? And that's where it comes down to whether you're talking about the left endpoint or the right endpoint or the midpoint. So this says, so first let's make sure in this example, let's find the area of 5 rectangles. In this case, the width of each rectangle is 0.4. Each of these distances there, and that distance, and that distance, and that distance, and that distance, and this problem happened to be 0.4. To determine the height of the rectangle, since we're finding the left endpoint approximation, it says to determine the height of each rectangle, use the height of the function at the left endpoint of each interval. So the first interval, here's interval A, B, C, D, and E. I happen to have 5 intervals, so I'm going to create 5 rectangles. Rectangle A, I've got, goes from 0 to 0.4. And since we're finding the left endpoint, however tall the function is at the left endpoint, which happens to be this height right there, that's the height of a rectangle. So I'm going to just draw that across and connect down. There's a rectangle that's supposed to connect. Rectangle B, again, the left endpoint, wherever the height is at the left endpoint, well, that's this height right there. I'm going to go across there and create a rectangle. I'm going to keep going. Rectangle C goes from 0.8 to 1.2. And the height of the rectangle will be however tall the function is at the left endpoint, which happens to be right there. Now, I don't know what decimal that is. I'll figure that out in a minute, actually. and I'll create a rectangle there. And then similarly, rectangle D, the left endpoint of this interval is right here. And there's a rectangle, and rectangle E, which go from there to there. So I'm going to find the area of those 5 rectangles. Now, as far as doing the actual math, I saved us the trouble. I did the actual math already. On this next slide, I've got the left endpoint worked out. So here's the math. Let's look at rectangle A. That picture should look very similar to the last slide. Let's make sure we understand what I'm doing in these equations here. It says the area of rectangle A. If all of these say 0.4 because all of these rectangles are still 0.4 across. That's just the width of each interval. As far as the height of the rectangle, clearly a rectangle's length times or base times height. Well, this distance from here to here, the height there is in fact the value of the function at 0, which is the left end point of the interval. So that's f of 0. And so I just remember my function was, well, y equals 5 minus x squared. That was my function. So I plugged in 0 to that. It turned out I got 5. That's where that 5 came from. That's the height of that rectangle. Rectangle B is still 0.4 in width. But as far as the height, to use my left end point approximation, this point right here, that y value is the function evaluated at 0.4. My interval goes from 0.4 to 0.8. The left end point is 0.4, so that's why this says it's 0.4. That's just the width of the rectangle times f of 0.4. That's whatever the y value is at 0.4. And again, I did the math. That turned out to be 4.84, and I multiplied it by 0.4. I got 1.936. That's the area of rectangle B. 2 is the area of rectangle A. Then I'm just going to keep going. Rectangle C goes from 0.8 to 1.2. The left end point is 0.8. So the height of rectangle C, which is this distance right there, is f of 0.8. However tall that function is at 0.8. So I do 5 minus 0.8 squared, which is where this 4.36 comes from. I do 0.4 times that, still finding the area of a rectangle. That turned out to be 1.744. And I keep going similarly for rectangle D. The height of rectangle D is f of 1.2, which is the left endpoint of that interval, which turns out to be 3.56 times 0.4 is 1.424. The last rectangle E, the left endpoint is 1.6, and f of 1.6 turns out to be 2.44. So again, I do 0.4 times that. I get 0.09 or 0.976. I add up those 5 areas, I get 8.08. That is the left endpoint approximation of that region. Now, clearly in this estimate, my approximation is too high because every one of those rectangles is bigger than the actual area. I don't want you to think that the left endpoint approximation is necessarily going to be too high. Clearly, if the curve would have been going up like this, and I had some intervals, my left endpoint would have gone from here and gone this way, and then would have gone this way, and would have gone this way. So just don't assume left or right having to be over under. But and actually, if the function were to both rise and fall, if the function were to look like this and this and this, one left point rectangle might be an underestimate, and the next one could be an overestimate. So there's no rhyme or reason. Now, since our original function is strictly decreasing, it turns out that the left endpoint approximation will be an over approximation, but it is an approximation of the area. Now, the thing I'll point out quickly now and dwell a little more later is what I hope you can see here is that if I instead of using 5 intervals, used 10 intervals, my approximation would be a little better. Like there would be a little less error if I had skinnier rectangles. Something to keep in mind. So there's my left endpoint approximation. Well, now we're just going to use the same region. Now we're going to find the right endpoint approximation. Well, it says to find the right endpoint approximation, we use the height of the function at the right endpoint of each interval to determine the height of each rectangle. So I drew it again. This time you'll notice that for my intervals are the same, 0 to 0.4 and 0.4 to 0.8, etc. But this time the height of the rectangle is how high is the function at the right endpoint. So for instance, rectangle A, remember the left endpoint started at the 0.05, went across the top at 5. This one starts down here at whatever f of 0.4 is and goes across this way. So rectangle A is 0.4, that's still my width, times f of 0.4, which is this y value right there. Turns out to be 1.936. I wanted to also make sense that that very rectangle, this, let me highlight this in green, this mass right there, 0.4 the width times 4.84, that's rectangle A using my right endpoint. If I go back a couple screens, that same 1.936 was rectangle B. When I went from there, that same point right there, this time I went as the left endpoint approximation. I went to the left, it was too high. But these y values, which are these right here, all these ones in the middle, we're going to use these again, because if it was a right end point one, it's now the left hand point, or vice versa, I suppose. Notice the 2 here, that we're not using. We're no longer way up here at 5 going across. We're not doing that with the right input. But a lot of these areas of rectangles will overlap for left and right, because the same y value in one direction is the right, the other direction is the left. So going back here, so then rectangle B started there, went across. So again, that y value for B is f of 0.8. There's that. And again, these decimals are just me plugging in those decimals into the function y equals 5 minus x squared. So again, I have areas of rectangles, rectangle B, C, and D, and those numbers all look similar. You'll notice area E is a different number, only because for E, we're using this height over there, which is f of 2, which we didn't have to use when you did the left end point. So that turned out to be that rectangle there. We add those together, we get 6.48. That's our right end point approximation of that region. Again, for this particular curve, since it's decreasing, it is an underestimate, but it's an estimate. But again, I'd like you to see that if I broke those 5 rectangles into 10 or 20, I would have less error. It would be closer to the actual area under the curve. Just keep that in mind. So that's the second one. Third one is a midpoint approximation. Well, you guys have cracked the code now, so you figure out what we're doing. To find the midpoint approximation, we use the height of the function at the middle of each interval to determine the height of each rectangle. So for instance, let me go back to a blank drawing here where I show you the one I did. Interval A went from 0 to 0.4. My left end point used the height of the rectangle at 5. My right end point used the height of it right there at 0.4. My midpoint is going to use the one right there. It's at the middle of the interval. Like it's going to, in this case, going to be a little bit above, a little bit below. I'm going to take the middle of the interval and go like that and make a rectangle from 0.8 to 1.2. The middle of the interval is right there. That's the height of this rectangle. Next one goes right there, and that's the height. Next one goes right there, and that's the height. Now you'll notice for this function that's strictly decreasing, notice the error here is it's better because now my mistake, for lack of a better word, is partly above and partly below. So it's probably a better estimate, but that kind of depends on the curve. Again, I've got this all worked out. Here's the midpoint approximation, having done the math. Notice the height of these rectangles right there, and there, and there, and there. My pen's not working very well. And there, that is like, for instance, rectangle E. The interval goes from 1.6 to 2. The midpoint is 1.8. So rectangle E is 0.4. That's still the width of the rectangle times f of 1.8. Like it's the value of the function in the middle of the interval that determines the height of the rectangle. So again, I've got 5 areas of rectangles here, which sum together to be 7.36. And again, in this case, it might be a better approximation because some of the errors above, some's below, but that depends on the curve. Excuse me. And then the fourth one, I decided not to make us do the tedious math, but the fourth, you could also find trapezoids. I could just connect the actual endpoints, like I connect the point of the graph there and there, just connect it with a straight line. And of course, the straight lines are very close to the actual curve. And then just find areas of 5 trapezoids. I will remind you that the formula for the area of a trapezoid is this. The average of the bases times the height. So I decided not to make us do that. But we certainly could also use trapezoids. And the assignment we're going to have just has a left endpoint, right endpoint, and midpoint. So I want to show you just real quick. I'm going to find, I know what calculus we're imitating here. So I am going to find the actual area and just compare it to our approximations here. This was what, 5 minus x squared. Let's see if I go like that. Okay, so it turns out, so let's summarize this. My left endpoint was, that's midpoint. My left endpoint was, where'd it go? 8.08. And my right endpoint was 6.48. And my midpoint was 7.36. Okay. I just made a new slide somewhere. So my left point was 8.08, and my right end point was 6.48. My midpoint was 7.36. Turns out the actual area under the curve is 7 1/3, 7.3 repeating. So we don't know enough yet to find the actual area, but we're approximating it using left endpoint, right endpoint, or midpoint. Okay. And then really, so your assignment tonight just has just one each. One, find the left endpoint approximation, because all this math that I did that before I started making it. You'll have to do that, like plug numbers into the function and figure out what the height of the rectangles are. So these are a little tedious. We're only doing three, one each, right endpoint, left endpoint, midpoint. But the conclusion is this. It says, regardless of which approximations we use, the actual area could be found if there was a way to have an infinite number of infinitely skinny rectangles. Think about it. If I could break this not into 5 rectangles or 10 rectangles or 20 rectangles, but a bazillion rectangles, each one of them really, really, really skinny. But if I found those areas, I could actually find the actual area. And it turns out the whole concept of limit is going to show up here before we're done. Like, what's the limit as the number of rectangles gets bigger of the sum of the area of these rectangles? That's what calculus will help us figure out. Again, that's getting ahead of today's lesson. But that's where we're going with this. But for now, it's just using rectangles to approximate areas. Here's your assignment. That's not it. There it is. And there's only 3 problems. But I need you to not do what it says in the book. I'm telling you, for number 33, just find me the left endpoint approximation. And for 34, just find me the right endpoint approximation. And for 35, just find me the midpoint approximation. It'll still take you some calculating for each one. They'll take you 5 or 10 minutes per problem to do all the math and figure it out. But that is the plan. So that is it for 4.2. So we'll do this on Monday, and then we'll move on to 4.3 on Tuesday after the live lesson on Wednesday. So have a great beginning of your week.